All right, so our next example involves an x squared. So we're going to show that the limit as x approaches 2 of x squared plus 2 turns out to be 6. Now that shouldn't come as a shock, right? If I plug the 2 in, I would get 2 squared is 4 plus 2 is 6, so clearly have the right limit, but again, we need to use the definition to actually prove that that's the case. So we start off as before. Let epsilon be bigger than 0, and consider the thing that has to be made small, and that is the f of x minus the target term. All right, now in the last example, we were pleased when, after doing some algebra, we made what in that example was an x minus 4 term appear, because that was the thing we had control over in making it small. We're not quite there yet, right? So this is where a little bit of additional algebra comes in, but that's the difference of 2 squares, and so it factors. And now this is good news, right? The x minus 2 is the thing we control because x is approaching 2. So I can make this as small as we like. The x plus 2 term introduces a little bit of extra difficulty because as x is approaching 2, the x plus 2 term isn't necessarily getting small. So we approach this in the same way we did similar problems with sequential limits. And that is, we first take care of this by getting a bound on it. And we accomplish the bound by making use of a sort of intermediate delta, which we're going to call delta 1. All right, so let's let delta 1, really it can be just about anything that's a fixed number. 1 is easy to work with. So delta 1 is going to be 1. And that means if later on, right, I'm thinking of x minus 2 being smaller than delta 1, well, if x is within 1 of 2, that means x minus 2 is between 1 and minus 1. And that in turn means 1 is less than x is less than 3. And so 3 is less than x plus 2 is less than 5. So my bound on x plus 2 is 5, as long as I've restricted x to be within 1 of 2. All right, so now what I have is x minus 2 times x plus 2. That's less than x minus 2 times 5, and I want all of that to be less than epsilon. Well, from this point, it's not so bad because I can just divide both sides by 5. And this reveals what I'll call my second delta, delta 2. And then to finish up the proof, we arrange to satisfy both of these deltas at the same time. So I want x minus 2 to be within 1, to be less than 1, and I also want x minus 2 to be less than epsilon over 5. And since I don't know what epsilon over 5 is, to guarantee this, I just need to make sure I take the minimum of the 2. All right, so here's the formal proof. Let epsilon be bigger than 0. And let's take my delta sub epsilon equal to the smaller of the two that I ran into along the way. And that makes all of my inequalities happen at the same time. All right, so f of x minus L, which is x minus 2 times x plus 2 by our previous work. That is less than epsilon over 5 times 5 by our two bounds. Cancel the 5s. So we've shown with a suitably chosen delta, specifically the smaller of 1 and epsilon over 5, I can make f of x be within any specified positive real number of L. That means L has to be my limit, and that limit was 6. So that completes the proof.